guess nobody's there on the other end, but nonetheless, the benefit of people that haven't. Even with this light, you can see, I presume, yeah? Okay. So there are a few things that, points that I wanted to re-emphasize, or at least, make sure that you understood. Any questions on this? If I ask some general thing like that, you know, or let me be more specific. This is what I define as a conflict clause. And the conflict clause is defined as a clause that blocks this conflict. Okay. Why do you think that in what way does it block? Why do you think it blocks? Anybody? First of all, you know how it is derived. Let me get, that involves the using the cut of a thing. Even basic thing, you know how a conflict arises. You know how BCP works, correct? How does BCP work? Anybody else? That's not. Okay. What does BCP do? This is the BCP. Okay. When does BCP gets kicked? When does it gets triggered? Okay. So I started with the resolution, then I came with unit resolution. Okay. And then BCP does repeated unit resolution, which is technically, pragmatically, what it means is that if there are unit clauses, that's what, if there's a unit clause, then it has to be, that literal has to be either, that variable, it forces a decision on that, or it implies a decision on that, either true or false, and then you plug it in that value that is forced in the rest of the clauses, and then you propagate, okay? That's what BCP is. Now, when you do that BCP, you can, since the state of the clauses get changed, okay? They can either reduce to true or reduce to false, or they may just remain unresolved. Some literals may go away, but or it may be they even become a unit, okay? And that's, you keep propagating. That's what BCP is. And a conflict arises when any of the clauses due to BCP gets reduced to simplified to false. It's as though that's what maybe you were trying to get at, and that's what happens, okay? So it's like when you plug some ones and zeros in a Boolean formula and you simplify it and it gets used to false, okay? So that's what is happening here. It's only when that, so here there are no unit clauses, okay? And therefore BCP, doesn't have any effect on this. Now, when BCP doesn't have any effect, then you still have to, then you make a explicit decision, okay? That's what is being done here, which is you pick a variable and then decide whether to to put 1 or 0. That's what decision heuristics does, okay? You can do it randomly, you can use various heuristics, and that in all SAT solvers there are sophisticated heuristics that are used. The moment you do it, it's as though making a decision on a particular variable to be 1 or 0 is like adding a unit clause to it, okay? That's what it means. I mean, you are saying, oh, maybe making a decision on it will make it satisfy, okay? And that's with that hope you do it. And that's, once you do that, then you do BCP with F added with A, okay? That particular thing. So in this case, for example, that's what you kicked in. So there was nothing, and to begin with, at level 1, I made X is equal to 1, okay? Then that simplifies some of these things, okay? Still, there is nothing, BCP to do, okay, because they're all unresolved. Understand? You will have to, ask questions if want to do so, because there will be a quiz, okay, sometime in the thing, and this is one of the things that I'll you to follow. In any case, that's how all these things happening. Okay, x is equal to, as a result of x is equal to 1, nothing happened there. Okay, at that point, this implication graph, it keeps track of when unit clauses are created. Okay, that's when this kind of keeps track of how unit clauses are produced as a result of various decisions. So when x is equal to 1, at this point, nothing happened, okay? Because just these two got simplified and is still unresolved. Similarly, then you have to make a decision again. You make 1 on x8, okay? And in any case, so that will simplify this. Okay, once again, it'll simplify this alone, right? That's the only one. Still, no unit clause is produced, so there's no BCP. Correct? Okay. Any questions? No. Or that is how, that is the question as to how a conflict gets created is as a result of these things, and that's what this keeps track of. And only when you make a decision x7, then there'll be lots of, see, the moment you make it, this becomes unit, okay? This becomes unit, and that's what this says. And that then further, this also becomes unit. Those two, when it's put in, so this becomes unit, and there's a whole chain of things. And finally, there'll be some conflicting implied decisions on these set of things. X1 is already 1, X2 and X3. These are implied, and that when in C2 results reduces it to false. Therefore, what that means is this decisions that you made is no, okay? It does not satisfy, so you'll have to change it, okay? Now, in the original DPLL, all you did was you would then go up. You will flip the decision at the latest level and try the 0, okay? So in here, in the CDCL, analyze conflict, tries to learn something from the conflict, okay? Now I'm getting to this question of why. And the reason that you got a conflict was because somehow you ended up, as a result of these decisions and BCP, these two became this, X2 and X3 got these values that resulted in. So that this is can be one source of conflict. And that itself was produced because X4 became 1 after this decision due to some propagation of thing. So you could say that this is also a cause of that conflict, okay? That when X1 is equal to 1 and X4 is equal to 1, some clause, this will reduce C2 to false. Therefore, this assignment, will never produce a satisfying assignment. So is this set of thing. If you did a, cut here or a cut like this, okay, then this is also, or you could do a thing like this here also, like this. With X1, not X6, not X5, that's also a source of the conflict. Or completely to the root is this one, which has only, so you could, in order to prevent this conflict arises when you have X1 and X2 and not X3, if that is the decision that you're making, okay? Correct? That's what, when you plug that value in, you got a conflict in C2, yeah? That reduced to false. Therefore, the negation of the conjunction of this particular assignment will block it, okay? Correct? Because that is what is implied by this thing, and that's how you do it. So that's how, because it is the answer to my question would have been okay, that the negation of this, because this cube, you, the dual of clause is a cube, okay? Cube is just a conjunction of literals, yeah? So because x1 and x4 resulted in a conflict, not x1 and not x4 is a conflict clause, is something that blocks the current conflict, okay? Now, this is kind of a, among all the various conflict clauses, this one which has something called a unique implication point, okay? It has some explicit decision, okay, some set of explicit decision, and it has, among all the implied literals that were produced with BCP, it has only one of them, okay, here, okay, or at least the current decision at the current level. You see in this clause, there is earlier decisions, explicit decisions made, but only one literal from the current clause, current level. That is called, that's a special kind of a conflict clause, because if you flipped the decision of this, it'll force a decision on x4. There'll only be one in the current level. Similarly, this conflict clause that has x1, x8, and x7 is also, that is usually called an asserting clause, okay? That if you flipped one of the decisions, then it'll, or in this case, for example, if you backtrack to x1, okay, and then if you kept that x1 to be 0, it'll automatically, you see, if this thing is added, once you backtrack, say, normally you would backtrack to 3, and then if you kept the decision, if not x1, it'll force this one to be the right value for x4, okay? So that's why sometimes you pick this kind of a thing. So what I'm going to show you is now, so what this CDCL, unlike DPLL, does is it learns the cause of that conflict and adds this learned clause, which is the conflict clause, which will prevent some, source of this kind of, that produce this particular conflict. And after that, you have a choice, okay? Once you have learned, once again, you will have to backtrack, okay? So the other aspect of CDCL is, rather than backtracking like you used to do only to the latest level, you can jump levels, okay? And the non-chronological backtracking, what it does is it looks at the conflict clause, okay? What it says is you backtrack to the level corresponding to the latest level among all the literals other than the current level that is in the conflict clause, okay? In this case, x4 was an implied decision made at level 3. So other than the current level, and there is only one other literal here, and therefore that is x1, which was a decision made at 1. It says, jump to non-chronologically to level 1, okay? There's no reason that you will have to do that. And that is a heuristic, okay? Because the reason is, anyway, you got this conflict, as a result of the earliest one. So maybe since you've learned something as a result of the decision, you might as well go back, okay, to that level and try. Maybe then with the new thing that you've learned, you can put that to use better, okay? But nonetheless, maybe even with this conflict clause, even if you backtrack, you may be able to find a satisfying solution, but that is what it is. When you backtrack to that level, I want to see I'm just going to show you what happens when you backtrack, non-chronologically, okay, to level 1, okay? Whenever you backtrack, just like if you backtrack to this level, you would just, flip the decision. When you backtrack, you will undo all the other decisions. If you skipped level 2 and 3 and backtrack to this, obviously you will be undoing these decisions, okay? Which means that you will have to get back these clauses into how they, they were prior to you made these two decisions. All these things will be put back. Okay, and that's what happens. So what does that do? Okay, so I'll keep this here. Okay. Release. Come on, come on. This thing is so sensitive. Okay, so you backtrack to this, okay? So you undid that. So X1, you still keep it, okay? So with this new learn thing, you will keep X1. So since you kept the decision on X1 without, what will happen? Immediately, X1 is 1, therefore this simplifies and it makes the right decision for X4. In the sense, not, it makes X4 to be 0. Okay, what this is saying is that it makes the decision X4 to be 1. After that, then, so C3 goes away, then you rework your thing, and that's what it says. Okay, so you backtrack to that, and then you keep this, and with the new learned clause, then if you make the same decisions, X8 and X7, believe me, what will happen is it'll reduce and then create another conflict here. Okay, and I'm not going to work through the whole thing. Okay, but that's how CDCL works. Okay, with the new learned clause, you backtrack to that level. Okay, that is the latest among all the literals that other than the current level, and then you rework your thing. But what will happen is at least this conflict of that was there due to X1 and X4 simultaneously being 1 would have eliminated. How does that get eliminated? Anyone? I just told you, okay? Because since you added this, it will force this to X4 to be 0. Whereas earlier, both X1 and X4 were being made to 1 because of these decisions. It turns out that there is another clause which also produces this thing, because even with X4 is equal to 1, there is a way that if it turns out that both X5 and X6 cannot be 0 together as well, okay? Therefore, so there could be several reasons for this particular, there could be several different conflicts for these explicit decisions that are made. That's another reason why it says, why don't you go back, skip and then go back to your earlier level, so that you will learn as many things that could potentially go wrong as a result of the decision that you've made earlier. Okay, that is the reason this heuristic also works in a case. Now, and that's what happens. Then you will then there'll be a conflict. Believe me, you can work your way through. There'll be conflict because both of them cannot be simultaneously 0. There is some other reason why it'll end up constructing a conflict. Now, for that, your conflict clause that can prevent is this one, because that has the unique implication point. So when you add that with that is not of X1 or not of X8 or X7, okay, that will be another learned clause, and after that it will produce a satisfying solution. That's how CDCL works. The key takeaway is that the difference between CDCL and DPLL is for every conflict, it analyzes that and then adds a new clause to prevent that. It skips level and then repeats the thing. Now, one can say Now, even if you backtrack to just this level and continued, you could have produced a solution, okay? There is a satisfying solution that you will produce, okay? So you could say, why do you skip to this level when you could have found something right there locally, a satisfying solution? So yeah, I mean, there's an argument to be made why do it, but as I've told you, even though there might be other solutions with this new fact right at this level, still this heuristics based on practice seems to be a winning heuristic in a lot of cases, and therefore they use chronological backtracking, okay? So two concepts that I want you to, as a takeaway here. One is how, what is conflict clause, how this CDCL works in terms of non-chronological backtracking. That I want you to kind of understand, okay? As a result of, after this thing. Now, how these conflict clauses, as I told you, any cut here that completely separates the conflict side from the non-conflict side. By a cut, I mean when I do this, all the sources that the edges being eliminated, that set of literals, the negation of that will form a conflict clause, okay, and so on. So that is how you do it. But there are other ways, but at least the concept of implication graph, the purpose of it, I want you to understand. Now, any questions before I move on? Okay, yes. Yeah, that's the only thing. I've analyzed conflict exactly does this. Constructing these conflict clauses, backtrack exactly implements that strategy that I just now mentioned, which is skipping levels. Okay. Now, briefly, I will give the context of what come on. No. This is not the one that I wanted. Keep so many. Is this the one? End up keeping so many things open that sometimes I get confused myself. This is the one that I wanted. Okay, this is just to give you a context as to where we are and where we are headed. So, I'm not going to discuss in this course all the internals of SMT, but some critical things that you need to understand to be able to see how some of the developments that have been done to specialize these things for DNN verification. So where we are right now, we kind of discussed this one, okay? There's a slight variation of the DPLL that works with these theories. Like you said, for DNN application, it is not enough to just be doing with propositional logic. Why, some of you? Why propositional logic not enough? Sulagdam. Well, no, let her give her a chance to answer. Why? Because propositional logic, Sulagna, has only true and false, okay? Now, in DNN, what are the inputs? Real numbers. Real numbers, okay? So, when you want to verify, you can have things like this, okay? You want to check if something is some algebra, some linear arithmetic combinations, because those are the kind of computation it does, okay? So the kind of formulas that you want to verify can be, will have linear arithmetic expressions or even nonlinear arithmetic expressions. You have a question? That is, I'm here giving all kinds of theories, okay? SMT solvers, they support not only linear arithmetic, which is the uninterpreted function, which you have a little bit talked about. This greater than is C. Bit vectors, bit vector operation, shift operation, okay? So these are these individual things, okay? Checking if satisfiability on a set of linear inequalities, etc. Okay, they are relegated, that's what I call as theory solvers, okay? For every theory that you have, if you have real number, linear, arithmetic over reals, then you need a theory solver for that, okay? Similarly, if you had bit vectors, you need a theory solver for that, okay? It needs to check under the, for those things which are satisfiable, which are not, yeah? That's exactly right. That's correct, okay? Eventually, all formulas produce only 0 and 1, okay? That is true. But the variables that occur, for example, saying 2x plus 5 is greater than 5 and x is equal to gy, that is what you want to check. Now, that will have to check whether 2x plus y is greater than 5, whether x and y are reals. They are real numbers. Therefore, you need something special, okay, some other thing. Just propositional logic will not be enough. And that's why SMT solvers combine, there is a layer which does the propositional part of it, this and this or this, okay? That, the propositional part is what it uses CDCL for that, okay? But to check if 2x plus y greater than 5 and x minus 5 is less than 0, is that satisfiable? That is a conjunction of linear inequalities over where the variables are ranging over real numbers. That is called the theory of linear real arithmetic, where the coefficients are all rational numbers, okay? That's what that theory is. So a theory solver, so what SMT does is it is a layer that is taking care of the propositional layer, but it uses solvers, I call them solvers, that can decide conjunction of formulas, atomic formulas, obtained from that particular theory, okay? So the various Boolean combination is done here, but what it relies on is a solver, like an LP solver, okay? A linear LP solver is something that can decide, given a conjunction of inequalities, linear inequalities, whether it is satisfiable or not is what it decides, okay? Now, but it supports any Boolean combination of those kinds of things, and that is taken care of by a DPLL layer. And we saw just a thing of CDCL is the technique that is used. Now, what I'm going to show you is one such theory solver that is able to decide conjunction of linear inequalities. And that's what LP solvers do, okay? And there are several algorithms, and among them, there is this algorithm called simplex, okay? And you must have seen in optimization course, etc. Simplex, how many of you know simplex? Okay, so because that is so central to being able to analyze DNN, okay? I mean, because they manipulate, therefore, I'm going to introduce you simplex. And then there is, the next thing is a kind of variation of, I mean, enhancement, you could say, of simplex called reluplex. That is one of the first tools that are developed for specifically for DNN verification. That's the route I'm taking. Okay. Now, with an LP solver, a theory solver for linear, or they even have nonlinear arithmetic. Z3 supports linear as well as nonlinear arithmetic solvers. Okay. And that combined with DPLL, that's why you're able to verify DNN. Okay. And you are, as your part of your second assignment, you're going to be doing that. Z3 is very powerful in this thing, okay? But it's a general purpose solver, okay? So the idea when they apply for DNN is to develop specialized solvers. There's always general purpose versus specialized. Sometimes specializing it to particular application gives you more efficiency, okay? And that is what reluplex does. That's what dpoly does. That's what alpha beta crown does, okay? You know, these tools do. And that is our next step. But, you know, so I want to, yeah, I'm going in this way. So I'm going to be just discussing LP solver, yeah. And simplex method for that, yes. Correct. Yeah, I think I see what your point is. Suppose your formula is suppose you had something like this, okay? That's what you're able to do. What the theory solver does is, if you type this into an LP solver, no, okay? Because it accepts only, it can check if this is satisfiable, it can check separately if this is only conjunction of linear inequalities, okay? Therefore, that's why this is called an extension slightly of DPLR called T, okay? It is able to query these theories for conjunction of these things. Now, when is this solvable? Either this is satisfiable or this is satisfiable. So one naive way of doing it, if you had a solver that is able to check conjunctive fragment, that's what I call, okay, LP. All theory solvers here assume to be able to check conjunctive fragments of that particular theory. What do I mean by conjunctive? Nothing, just a conjunction of those atomic formulas. Therefore, one naive way of doing it is, oh, I will just take this in some CNF form and I will check each of the conjunction. Okay, if I'm assuming you can always express any prepositional structure as a disjunction, a sum of conjunction. I can check each of them, for which I can just send it off to an LP solver. Okay, you can do better than that. Okay, that is a naive way of doing it. Okay, and you can see that if you want to express any formula in this fashion, it can be exponential in the size. Okay, any Boolean function. Therefore, that doesn't work. Therefore, what Z3 does is it's a closer integration of this and this level. Okay, so we may not be able to get to that particular thing. And what reluplex does is, that is the idea that it uses, okay? First, we will discuss simplex, okay, today. And then what it does is it kind of shoves this into simplex, or you can say that it extends simplex to be able to do such or thing in a more efficient way than simply checking each of the conjunctive fragment, which can become exponential. Do you understand why that method of naive method doesn't scale? Because if any formula, Boolean function over linear arithmetic of that kind, if you want to reduce it into a DNF or CNF form, which is what that is relying, that size can be, the conversion itself will increase the formula exponential size, and therefore you will have to check You have to make exponential number of calls to this theory, and that does not scale because we want verification methods that can scale, okay, to real DNN size. And that's why that. So that is the context, okay? Any questions? Yeah. Exactly right. Exactly. Yes. Yeah. Yes. Yes. So I mean, yes, DPLLT. See, the simple DPLL that I discussed, that I showed just now, assumes that the atomic formulas are just prepositional, whereas here your atomic thing can be something like this. Okay. For that, the DPLL itself doesn't know that. It actually, one version of this, you can replace, I'm sorry, this must be some less than or equal to 1 or something like that, okay? Each of this is a Boolean predicate, gives 1 or 0. You can say, I'll just make it B1, B2. The DPLL can solve that, okay, like you said. It doesn't care about what the thing is. Now, this is always satisfiable. It says, oh, I know that I can make this true if I make B1 and B2 to be true, or B3 to be true, and B1, B2 to be false. The question is, if I make B1, B2 to be true, when I expand them into as real numbers, are they still satisfiable? At the DPLL level, this formula is obviously satisfiable if these two things are true. But when you expand them into this may not be satisfiable as a real when you interpret them on real numbers, because x greater than 0 and x less than 0, obviously it's not satisfiable. Okay, that is what it has to check. Okay, so for every such satisfying instance at the DPL level, it has to check. We are going away from that, okay? That I will get to, okay, when I talk about ReLU-Plex, okay? Hold your thoughts unless if it's a brief question, okay? Yeah. Then well, if it is nonlinear, it has to rely on a nonlinear solver, okay? I mean, as a matter of fact, the theory, the nonlinear theory over reals is decidable, okay? It's quite efficiently solvable, okay? So Z3 has a nonlinear real arithmetic solver, but only the conjunctive fragment. It relies with the DPLL structure for the non-conjunctive fragment. So it needs some, at the theory level, it needs some nonlinear thing as well, okay? Or there are techniques where you could somehow eliminate the nonlinearity, okay, in some cases, and it may use those kinds of tricks. But in general, it needs, it relies on a theory solver, whatever theory that you want to solve it over. Okay, so that's the context. Yeah, this is just the syntax. What we are talking about is just linear arithmetic. Okay, that's all. I've just given this in a syntactic form. So it can be some conjunction, only conjunction, okay, of, say, only conjunction is allowed. That's what simplex or LP solver solves. And there'll have to be expressions of this kind. You can have plus and so on, with rational coefficients, x and y can be reals. Okay, so first I will set, some of the things. Simplex is some historical things. I mean, generally LP, the way that we use it, LP solvers, generally have, in addition to, they take as inputs a set of, set of linear inequalities, okay, which means they all have to be simultaneously satisfied. And they also take an objective function. Among all the solutions, it needs to generate a solution that is, that optimizes this thing. But since we are interested only satisfaction in our case, okay, so it does not have the O, and it just has to produce an assignment that satisfies it, which kind of simplifies the problem a little bit more. Simplex is worst case exponential. There are other methods, Fourier-Motzkin and ellipsoidal thing, etc. But in practice, it turns out, in practice, an expected thing, this simplex outperforms all things, and that's why most practical tools use only simplex algorithms. Okay. Yeah. Now this ignore this comment for now. So how exactly the interface of that interface with DPLT is something that we can get to later on. Okay. We put the whole thing. Okay, so this is the input that you have. Some linear expressions, okay, which are inequality, can have lower and upper bounds. And this is transformed into set of, we introduce a new set of these, we can call this as the original or program variables or primary variables that are in the original formulas, okay? And then you introduce a new variable, it's called some additional variable or slack variables for each of these expressions. You equate them, okay? And then, so that these are just equalities, equating this slack variable to the corresponding expression that it stands for, okay? And then you specify the bounds on that slack variables, okay? Is that clear? So this transformation is correct, right, Sulagna? Okay. So this is simple. I mean, I'm just introducing and equating them and then things. So that, in theory, X and Y, the program variables, are unconstrained. They can be ranged from -infinity to +infinity, but the constraint is kind of indirectly imposed on these expressions. Yeah. So even if there are constraints saying X must be less than or equal to 2 or something like that, you can say in theory you could introduce a new slack variable and then make X unconstrained. Okay, so technically speaking, whether you want to implement that or not. So, but that for convenience, and then a newly introduced, and therefore you want, if you take this, so there is this a matrix A, which you could represent these things as. So, for example, there is a bunch of equalities. That's what there is. Okay, and then you can say that the problem that you want to solve is you have to always preserve that AB is equal to 0. These equations have to be preserved, and you will have to check if there exists some instantiation for the XY variables, so that equation is preserved, and these constraints on the slack variables are preserved as well. Yeah, understand? Yeah, I mean, you could represent in this case A like this and so on, but you can also preserve them as, keep them as equations like this and so on, which is what I guess it's hard to read for you. Shall I put one at a time, or anyway, so you'll have to come forward like me. So I mean, yeah. So you partition the variables into, okay. So we have now set of variables. Okay, primary variables or program variables and additional slack variables. Okay, the slack variables are the ones that are constrained with some fixed lower and upper bounds. Okay, and the problem is to check if there is a instantiation for all those variables such that all these equations that define the slack variables in terms of the primary variables as expressions, that equation is satisfied while preserving the bound constraints on the thing. Now, this AB is equal to 0, as I said, you can also express it as just an equation. we're equating those slack variables to those expressions. And that is sometimes called is called a tableau, okay? And that is what is maintained by simplex. And of course, each slack variable has lower and upper bound constraints. That's also fixed, okay? And the thing, this tableau is fixed, but it kind of changes, okay? And then, so for example, in this case, this tableau is, yes, in the beginning, it will be like this, okay? So when you write this, now, what simplex does is, through its procedure, it kind of, so this, we call the entire set of variables as program variables and slack variables. Now, moving forward, we'll not distinguish between those two things. But that set of variables in the, this is what is called an LP, okay? At least the part LP instance of the problem. Now that is partitioned into a basic set and a non-basic set, okay? Now, at any point, the basic set, the variables, the set of variables that are pre-variable, I mean, the primary variables and slack variables, I call that as the set of variables. Some subset of it will be in the basic set and others in non-basic set. Now, for example, in the beginning, the basic set consists of all the slack variables, okay? So you can say these are, in the tableau, if it is expressed as rows, all the ones on the left-hand side of the equality there, that is the basic set of basic variables. And the ones in the column here, they are non-basic variables. That's how you start with. Rows denote the current set of B variables, the columns variables. And you see in the simplex procedure, you keep moving these variables between basic and non-basic, okay? Now, to begin with, obviously the only constraints are on the basic variables that have to be satisfied, because the non-basic variables are unconstrained. To begin with, they are primary variables. So what it does is it picks one of the, if one among the basic variables which violates its bounds, okay? There can be more than one. Some of them may already satisfy. Okay, there is some, it begins with an initial assignment. Okay, that's the thing. So initial assignment could be just zeros, okay? You can pick anything. Let's assume that it is zero. So this is the basic operation that it does, okay? It picks a basic variable that violates one of its bounds, either lower or upper bound. And fixes it to satisfy its bound, okay, by adjusting one of the non-basic variables, okay? So in this case, either X or Y. And it does that such that it, you see that it just adjusts these variables just enough to bring these non-basic variables, okay, to its either lower bound or upper bound. So if they're violating, either the current value of that basic variable could be less than its lower bound, or it could be greater than its lower bound. Oh, by the way, this algorithm that I think that was there in the previous thing that I ignored. Okay, so equality can be expressed as less than or greater than, but then this procedure that I'm going to describe works only for non-strict inequalities, like less than or equal to. There is some extra enhancement that you'll have to do strict inequalities, okay, which I'm not going to discuss it in the thing. And the other thing that I wanted to check, which I will load, which I think I said right in the beginning itself, I'm relying on these things. I will upload both of these things. This is a very good paper, okay? So, you know, so at a high level, this textbook is a chapter in that textbook. So on SMT solvers is very nice. And that itself is based on this paper. This paper has some proofs, etc., of correctness of simplex algorithms. If indeed some of you want to go look at it, I only will give you a sketch of it, okay, maybe towards the, if I'm able to get to it. But those are the two references that I'm using for the thing, and some of the pictures, etc., here are actually borrowed from those two papers, and I will upload them. Okay, and that's what it does. And the basic operation that simplex uses is this pivot and update operation. It picks a non-basic variable, which currently, based on the current assignment to it, to the variable, it violates its bounds, and then adjusts, picks a non-basic variable to change its value, to adjust this just enough to move it either to its lower bound or to the upper bound, okay? And then once that is done, it pivots those two variables, okay? It moves the this non-basic variable, that is the basic variable that is fixed, to into non-basic, and then that one. And that thing is what it, yeah, that's what it does, okay? So that operation is called pivot and update. And once it is done, you will have to kind of move around, change this equation so that the basic, the current basic variables are always on the left-hand side of the equation. So, for example, here, if you start with this and with these constraints, S2 violates it, and therefore I'm changing the value of x to fix, adjusting the value of x to fix S2, and after that I will rearrange the variables in here. So in general, yeah, so the way it is, because these are linear equations, so the basic variables are sometimes also called dependent variables, because they're always arranged in such a way they're defined in terms of the non-basic variables. And the one invariant, okay, after every step, so in the beginning, because in the beginning, this tableau, the non-basic variables are the primary variables, which are unconstrained, okay? Which are unconstrained. So the pivot operation always, so the non-basic variables always satisfy their constraints, okay? That is throughout, the simplex preserves that, okay? Because it's only the basic, one or more of the basic variables might, might be currently in violation of their bounds, okay? So before it moves it, using the pivot operation, it always fixes it and then moves it, okay? As a result of adjusting this thing, sometimes you may make the value of the non-basic variable, move it out of bounds, and that's why you pivot it into the basic variable. So the key thing is non-basic variables throughout the simplex algorithm, they always preserve they satisfy their bounds, okay, in the beginning as well as in the, so it's that is the thing that is preserved, okay. So the procedure repeatedly, I'll give details of these things, repeatedly performs these pivoting operations until there are no more basic variables that none of the basic variables or all the basic variables satisfy their bounds, okay? The non-basic variables always preserve their bounds, okay? It's only the basic variables, one or more of them, they may be violating their bounds, and that you fix by picking one at a time, okay? One basic variable to fix, one non-basic variable to adjust, okay? And then, because in the process, the non-basic variable, you might be driving it out of its range, you put it back. And you keep repeating this until you get to a point where there is every basic variable satisfies its bounds. Okay, then you have both the basic variable and non-basic variable satisfying, their bounds, okay? And therefore, you have a satisfying instance. And then at any point, if you are not able to make progress, at any point you have At every point, you have a current assignment for the variables and a tableau which defines what are non-basic and what are basic, okay? And yeah, so you may get to a point where you still have some non-basic basic variables which are violative of their bounds, but there's no basic non-basic variable to adjust, okay? Then you declare it is unsatisfiable. Okay, so that is the idea. Okay, the basic. Yeah, this algorithm, as I said, it's a place for non-strict, only for non-strict inequalities. Some more details. Okay. Yeah, the other thing it does is, okay, firstly, this is the state or configuration maintained by the simplex procedure. There's a tableau, okay, which is uniquely defined once you fix the current non-basic variable, set of non-basic variables and basic variables, okay? The basic variables are just defined in terms of the non-basic variables, so that there's an equation that is thing. So the tableau can change because the non-basic variables, the set of non-basic variables and basic variables keep changing throughout the simplex procedure. So T is each row in this tableau is a linear combination of the, the original equation that I had. So there, the current basic variable is defined as a linear combination of the non-basic variables. The B is the set of variables and non-basic variables, okay? And once you fix these things, this tableau is uniquely defined. And then there's a variable assignment at any point. So there is, you start with an initial assignment, which we assume it is 0. And then you keep updating beta through the pivot and update operation. And therefore that will be changing. There are lower and upper bounds, fixed lower and upper bounds for each of these slack variables. Okay, so that's also fixed. In addition, you also use a fixed order, a strict order on the variables. Okay, there is a fixed order on the on all the variables, the program, the primary, and the thing to consider. Okay, when you do the pivot operation. When you do the pivot operation, you have to pick one basic variable that violates its bounds. If there are multiple ones, which one do you choose? Okay, you choose the lowest variable in that order, in that strict order. Similarly, if there are multiple ways to fix the basic variable, multiple choices of the non-basic variable that you can choose from to adjust to fix the basic variable, then so you have a choice, and that also is and you choose, and it says that you have to choose the lowest one. Okay, this is important as you'll realize, to use that strict order. Otherwise, this procedure may not terminate. Okay, so you may kind of flipping back and forth, and it may never terminate, and that is that's the reason that you will have to use that that strict order. Yeah, as I said, the initial state will assume in the initial state, the program or the primary variables are all the non-basic variables, so they all satisfy their lower and upper bounds because they are unconstrained. The initial, the slack variables form the initial set of basic variables. Okay, so some of them, yeah, and then you assign all of them to 0. Yeah, this is a reproduction of the algorithm as it is described in that paper, and it's also the way it is in the text book as well. Like I kind of said, you select the smallest basic variable that violates its lower upper bound. That is x such that either in the current assignment xi is less than the lower bound or greater than the upper bound. 0, all zeros. Okay, I think there may be various other things that you could do. Probably you could do, I mean, but let's assume it is 0. I think it works for any other assignment as well. Okay, so you pick the smallest variable that violates its bounds, okay, either of its bounds, And then, yeah, if there is no such xi, that is then it is satisfiable. Okay, the current assignment is satisfiable. Now, if it is violative, then there are two cases, right? It's either less than the lower bound, okay, or it is greater than the lower bound. Those are the two cases. If it's less than the, if it's less than the lower bound, then you select the smallest non-basic variable exchange. Smallest means in that order, okay, the strict order that I said, such that, you have to, if it is less than Li, you have to increase it, okay? These variables are, the variable that you pick, the non-basic variable to adjust is called a positive slack. You have to pick a variable that has a positive slack. That means it can allow you to increase the current value of xi to bring it to and make it equal to its lower bound. As I said, you'll only increase it just as much as you need to, okay, in the thing. So that depends on if the coefficient in the tableau that defines xi, the basic variable, if it is positive, then you will have to pick something which is less than its upper bound, because that's when, in order to increase it, if the coefficient is positive, you have to increase the value of the slack variable, the non-basic variable. So, but it better be less than that. There must be slack there for it to do it. The thing is, as long as it's less than its upper bound, you pick it and you adjust it as much as you can. That's why, as a result of which, you may drive the non-basic variable beyond its upper bound, okay? So that's why you pivot it, okay? But that's the thing. So this one, or if it is negative, then you have to decrease it in order to increase. You have to decrease the non-basic value of the non-basic variable in order to increase the basic variable. Yeah? No. No, there's no heuristic at all. This is all uniquely defined. As I said, I always increase this value of xi to bring it and make it equal to lower bound, okay? So therefore, you know exactly by how much you will have to increase this xi by. And then you adjust the current value of the non-basic variable just by that amount. So that, because you know what the current assignment is, you know what the lower and upper bounds are, they're constants, so you know how much you'll have to exceed by. It's actually a beta xi in this case, beta xi, no, Li minus beta xi, okay, divided by aij, okay? That's what you will have to adjust it by. So it's easily calculated as a fixed amount. There's no uncertainty there, okay? The only uncertainty is which variable, non-basic variable you pick to adjust, yeah? Yeah, you can use any order. Now, different ordering, as we'll see when we discuss an example, can produce different solutions, okay? And, but no matter what ordering you choose, you always produce a solution, okay? And after you describe it, to actually prove as to why this simplex works is non-trivial, okay? But it works. This is, proof that it really works requires some thought, okay? And I'm not going to cover that. I'll give you some basic idea of how the proof works, and I'll refer to you to that paper. So this is the, okay, that's all. So this is the dual of that, that's all. Now, the other important thing is, if there is no such variable, non-basic variable that is able to fix it, then you say, then no progress. Wherever there is no progress, you can declare it is unsatisfiable. Yeah, and this is just the dual. This is the case where you need a negative slack. You have to decrease the assignment. That's all. Yeah. Yeah, this kind of explains, gives your question. So what this does is, yeah, this is the flipping. Yeah, you modify T, that is one that you do by moving the, because you're pivoting, you have to modify the tableau so that you bring all the non-basic variable that has been pivoted into the basic set. And you modify beta by picking the value, because you always either bring it to make it equal to the lower bound, or if it is above the lower bound, you bring it down to decrease it to the upper bound, and you correspondingly determine that. Okay. Now, I think in order to understand this, it's better to view it why this works. View it the solution space in a geometrical way. Okay. So this is in a two-dimensional. Okay. If there are two variables, primary variables in your original problem, then your solution space, the space of solution, satisfying solution, can be described as a plane. Okay, as a closed. You see, it's a plane. So in a two-dimensional space, each equality in the tableau defines a line. Yeah. I mean, in general, if it's multi-dimension, that's the concept is called a hyperplane. Okay. Each inequality defines either a closed or an open half space, which is in a two-variable space is a plane. Like, for example, this inequality here, S3 being greater than or equal to 1, is all the regions that is above that line. Okay. That's a plane. This is a line. So in multi-dimensional space, this is dimensions. This is called a half space. Okay. So solution then is it's the intersection of these half spaces. Okay. So in this case, this constraint that S3 is this one is greater than or equal to 1, it exits all that space above that. S2 less than or equal to I mean, here the upper bound is infinity, so there's only lower bound in this example. So S2 being greater than or equal to 0 covers the space here. Okay, it passes through 0 here, and it is on this side. And similarly, S1 being greater than or equal to 2, it passes through 2 here, and that's above that line. And that intersection, it covers this region. Okay. Here, that's why I say that in this case, in general, in multi-dimension, it's called a convex, it's called a polytope, and it is convex. It can be open like this, or it can also be a closed one, okay? If indeed you have some other constraints like, I think it can be, okay? So that is the solution space. Of course, there is infinite, the space is infinite, okay? The set of satisfying solution is infinite. But simplex obviously terminates with the satisfying instance, so it cannot be searching that entire space. And the trick is that since it's always a convex polytope, okay, so there are these intersection points, okay, some subset of those intersection points of these half spaces, okay, are, I call them extremities. They are always they're always part of the solution, and there are only finitely many of them. Okay. So, for example, this is also an intersection point. Here, there is two things. I mean, this is one. I mean, you can have various intersection points. This one is not part of the solution. This one is this point C, and let's name this D. Those two are solutions. Of course, anything in here is also a solution. Okay. So what simplex really does is the solution, it gives a satisfying solution, see, when a point is on this, it's always at its bound, okay, one of its bounds. Okay, so if this point is such that S3 is at its lower bound, S1 is also at its lower bound, this line, okay, because it's the intersection of these two things. This is a point which satisfies S3 and S1, and that is at its lower and upper bound, okay. But S1 and S2, I mean, X and Y is such that S1 and S2 are at their lower bound in this in this case. Okay, I mean that's always the case. So what the solution that simplex finds is one in which some subset of these slack variables are at their extremities, either at lower and upper bound, and all the rest are defined in terms of those things. Okay, and there are only finitely many of them. Of these things, because there are only finitely many slack variables. There are only finitely many combinations of those things with lower and upper bound. So they're all finite, okay, because your solution is exists as some subset of those things, okay. The subset of slack variables are at the lower and upper bound, and the rest are dependent anyway, okay, as expressed as a linear equation. And that's why simplex, it restricts itself to searching this finite state space of solutions, okay? Yeah. No, in this case, all of them are greater than all strict inequalities, okay? I know, I'm not dealing, this version of the algorithm is not that, okay? Then you have to pick a delta and then do some clever things, okay? If there is interest, I can present the algorithm, but here it's inequalities, okay? So because it includes this line as well, okay? And that's why you're able to do that, yes, okay? So if it's strict inequalities, then this the line of argument that I just now said does not work. But obviously, you can also express it in terms of finite spaces. But I think you'll have to use some trick there in terms of how far it is from that strict inequality. So let me defer that. Okay, so that is. No, the convex is, I mean, this is by definition, okay? It's because it is the intersection of these hyperplanes, then it means it is, that's how convexity is, that, okay, you can see this intersection of half spaces are, by definition of half space, etc., they are convex, okay? There's independent definition of convexity, okay, that you can do, and that's what gives you these intersection points. They're kind of bound by a finite set of intersection points. Yeah, it's closed if the extremities are all finite. In this case, there are some thing, and I think that you can go and then check. Okay, this intersection of half spaces is a convex polytope. Okay. Okay, so here is how an illustration of how that thing works. Okay, so you are at here, you're starting a thing, and your starting state is tableau is all the slack variables are in the basic set. X and Y are the thing. So, and this is the variable ordering that I'm working with, okay? So these are the things. So in this state, S2 already satisfies its bound, correct? S2 has great, X and Y is 0, S2 is 0. Everything is 0 here anyway. So in this is the assignment. This is the tableau, and this is the variables the basic non-basic pair that you choose to pivot. Okay, and I mean you can hear S1 and S3 are both violate their bounds, and therefore you can choose either of them. But S1 is lower in the order, and therefore you choose S1. Similarly, you can either choose X and Y to fix this in this case, but X is in the lower, and that's why you do. And theta is the amount by which you will have to adjust X hereby. And that, as I said, is computed uniquely by this expression, okay? And then that's what you fix it by. So this is 0, and what you get is X is increased by 2 to bring S2 to, no, S1 to 2, okay? S1, the lower bound is 2. You just increase the slack variable, X, I'm sorry, not the slack, the non-basic variable here by 2 to bring S1 to just its lower bound. Yeah. So after you do that, S1 obviously will satisfy its bound. And then I mean, S3 and S2, since they are dependent variables, since X has changed, their values change, okay? So that's what, as per you plug in the new value for X, that's what you get here. S3 becomes -2, S2 becomes 4. So as a result now, S3 is violates its bound, okay? Because it has to be greater than or equal to 1. S2 is greater than 4. Yeah, that is okay, okay? So now here there's only choice is S3. So you can see that what is happening from A, you're moved to B, okay? You fixed S1 in the first pivot operation, pivot and update operation. And since it's the X and since you have changed X, you're moved to here. So satisfied S1. And S2 is all this area, so S2 is also satisfied. But S3 is the solution of S3's constraint is that, and that's why S3 is violative. So, and in the next pivot operation, you move from B to C, okay, which is a satisfying solution, okay. So that is the only solution that you know, that is possible for this variable ordering and thing. So of course, there is there are several. I mean, you can get to here also, and there are, okay, firstly, there are 2 solutions here, okay. I mean, there are infinite solution, but 2 solutions under the assumptions a convex polytope, okay. So because we are concentrating, if it's convex, then it is this extremities hold good, and the theory of why it has to be convex, you know, is intersection of half spaces and so on. So that we'll have to get into. So that is, yeah. And you can see, I mean, depending upon the ordering that you choose, you can get to a solution by actually going here, or you can go like this, then come here. That's one way of reaching it, okay, and so on. So that is kind of thing. If there is a solution, there is always, every time that you adjust, you're making these things always go, you know, X and Y are freely changed. Okay, there are several observations that you can make. See, once X, the primary variable, moves into a basic set, it stays there. Why? Huh? It's unconstrained, correct, okay? There's no constraint because it'll, you know, once you adjust it, that is the usual initial adjustment that you will make, okay? And that is one observation. And then once a slack variable moves from the basic set to a non-basic set, it's always set to either its lower bound or its upper bound, okay? Because you always adjust to its thing, and that's how you restrict. And that's why the state of solutions is finite. Once those basic set and the non-basic set, which itself determines basic set and its lower and upper bound. So those are the things, okay? And then the invariant after each pivot operation, it makes all the variables in the non-basic set always satisfy their bounds, okay? So here is another variable ordering, which moves this gets to the same point by actually moving it here. This is D, if I'm assuming A, D, C, okay? And as an exercise, I let you figure out an ordering that gets you to this point, okay? So it should be something that takes you here. I mean, you can guess now. So if you have to, okay, obviously, because if you move Y, allow Y to fix an S1, Y to actually adjust for an S1, you move the order here, then you can get to here. And after that, you'll have to kind of move the things around in order to get that, because with the original basic ordering, this will not get you to there. Okay, so I'll have to kind of leave. Yeah, I will just leave it here. Okay, so just look at the algorithm. Try to get various other solutions that you get there by playing with the ordering. So there are two aspects. Soundness is whether the simplex, whenever it terminates, this is true for any decision procedures, for any things in logic. If the algorithm terminates, if what the output that it produces is satisfying. Hey, can you tell me that? Ask him to wait here. That is soundness. And if it says no, it has to be unsatisfying. Okay. Of course, it has to terminate. Okay, termination itself is an important thing to prove. And usually termination comes as completeness. Now, does it produce answer for every input? Okay. So in this case, if it's an algorithmic, then it reduces to showing termination. So on every input, it has to terminate. When it terminates, whenever it produces a yes answer, it is indeed the solution that it produces satisfiable. And whenever it says no, it is unsatisfiable. These are the things that you will have to check. And I'll give you some intuition as to why simplex procedure always terminates. You must have already got an idea, because the solution space that it searches over is finite, okay? And if it's finite, the only reason it may not terminate is because if it comes back, if the same state recurs, okay? So the proof of termination involves showing that the same state does not recur. And that is where the termination ordering, I mean, the strict ordering comes to play, okay? Has a bearing. The other thing is, that when you terminate, if it is satisfying, if all the constraints satisfy, obviously it is a satisfying instance, okay? Because all the variables are within their bounds, okay? Basic and non-basic. The tricky part is, why should it always progress, okay? And when it does not progress, why? You could say that if you say unsat, it is indeed unsat. That is a challenging part of the proof, okay? So that we will see some intuition next time before we do check reluplex, okay? I still haven't done one thing. Now I'll have to give. I think I encourage you to start working on the part 1, part 2. I think he must have uploaded part 2 also. Part 2 is, okay, if he has not, I will do it. So I think please do it. And then I want you to actually be spending your midterm on my assignment, part 2, okay? So the midterm will not have an exam, but we'll have a quiz a little bit later on, because I want to cover at least, the part where Madhukar and Diganta, after my coverage and Madhukar and Diganta's thing, that is the kind of what I consider is the theory part of this course. After that, and that is what your the quiz and the assignments will test you on. Okay. So, and I'll give the quiz after that thing is covered. Okay. So you are free to leave.